Hello again, this is James Tierney from TierneyEducation.com. Got a question from one of my students about finding the total cost as a function of quantity with a Cobb-Douglas production function and not using calculus. So I'm going to give some information here and then we're going to dive in. The question sent to me gives us a pretty standard Cobb-Douglas production function where Q is equal to L raised to the 1/2, K raised to the 1/2. And we are given the wage is 36, which we can think of as the price of labor, and the rental rate of capital R is 4, which again is the price of capital. First, let's talk about what our overall total cost function would be if it was with respect to labor and capital. So if it was a function of labor and capital. This is our standard total cost function, which we've been using since our introductory econ class, where we know that it is wage times the number of workers, that would be W times L, added to R times K, which is, again, our rental rate or our price of capital times capital. So make sure you really understand this. My overall cost of production is going to be how much I have to pay my workers times the number of workers, plus how much is going to cost me for buying a piece of capital times how many pieces of capital I end up buying. Now, what we want is we want total cost as a function of quantity. Well, how are we going to do that? By the end of this video, what you'll have is you'll have L as a function of quantity, and then we'll do R times K as a function of quantity. So what we need to do is we need to find my L and K as a function of quantity. So let's begin. Now notice up here, I say this is without calculus, meaning I'm not going to require you to take a first derivative because that's how Penn State ECON 302, which is what this question comes from, does. But the main idea we still need to know kind of has some calculus in it. So remember, we need to have my MPK over R equaling to MPL over W. Or what a lot of times you'll see is you'll see MPL over MPK equaling to W over R. This right here, the ratio that we're going to need in order to minimize the cost. Now, if you remember from my old videos, I always have a rule for maximizing utility depending on the type of utility function. And I'll put a link up here in the top right-hand corner so that way you can check that out if you want. But these rules are going to be the exact same thing when it comes to minimizing costs. And this is what I mean by necessarily not using calculus, because I'm going to give you what the standard rule is, or it's going to be a ratio, what that standard rule or ratio is going to be with a Cobb-Douglas. So I'm going to scroll down slightly here, and I can give you that rule. So the rule I need you to know, or the ratio that I need you to know, is it's always going to be alpha over beta times K over L equals W over R. If you don't want to take first derivatives all the time to find MPK and MPL, you can remember this, and as long as you have your standard Cobb-Douglas, it's always going to be this ratio. So let's go ahead and plug in what we know at this point. Well, alpha and beta, which are the exponents to Cobb-Douglas, I should have said that before, but this is always alpha, what's on top of the, or what's the exponent for L, and beta is what the exponent is for K. So that's 1/2 over 1/2, which is equal to 1. We have K over L, which is our unknown, so those have to stay that way. And then our ratio W over R, 36 over 4, is going to be 9. So I know our ratio K to L is going to be 9. What I always do is I say, okay, what does that tell me? That tells me right away that K is going to equal 9 times L, right? That's just multiplying both sides of this equation by L. So this right here is your first step, step 1. And we'll go over these steps at the end. Step 1 is to get K in terms of L. by using this minimization rule. Now I'm going to scroll up a little bit again, so that way we have enough room to do the second step, which is going to be taking this right here and plugging it into our initial production function. So as a reminder, we had Q was equal to L to the 1/2, K to the 1/2. So what we're going to do is we're just going to plug in this K to this production function. So Q is going to equal L to the 1/2, and then we're going to plug in our K, which is 9L to the 1/2. I'm now going to do some algebra, and so we know this is Q is equal to L to the 1/2, 9 to the 1/2, L to the 1/2. I'm going to do each step out of the way just so everyone kind of really sees where this comes from. Scroll up just slightly to give myself a little more room. If I have an L to the 1/2 and an L to the 1/2, those are just going to be L. So I'm going to have Q is equal to L, and then 9 to the 1/2, that's the square root of 9, is going to equal to 3. So this is going to tell me L as a function of Q is going to be equal to 1/3 times Q, because I'm just dividing both sides here by 3, getting me to L, Q over 3, or 1/3 Q. And this here is L as a function of Q. So no matter what quantity we're looking for, I can plug it in here, and I'll know how many L is going to minimize that cost. So let's go up here. We need to find L and K as a function of quantity. We just did. Now we just have to do K as a function of quantity. Well, what do I know? I know K is equal to 9 times L. Okay, well, if K is equal to 9 times L, and I know what L is, I'm just going to say that K is equal to 9 times 1/3 Q. Well, this 3 is going to cancel, get us to 3, so I'm going to know K as a function of Q is equal to 3Q. So therefore, I have exactly what I said. I need to find L and K as a function of quantity. So there's my step 2. Again, I'll go over these steps at the very end of the video so that we have a nice, easy step-by-step guide to make sure you're solving one of these. Step 2 is to go ahead and find K and L as a function of Q now that you know what that ratio is from before. We only have one step left, so I'm glad you're hanging in there with me. I'm going to scroll this up a little bit to give ourselves some room. And our last step is to then say, okay, remember, I know my total cost as a function of L and K is equal to W times L plus R times K. It's always good to write that out every single time so that we remember it for whatever exam or assessment that you have. Now, we're going to take total cost as a function of quantity by plugging in everything we know. Now, I remember W was 36. L, which is right here, right above us that we already have, L is equal to 1/3Q plus K is over here. So K, we have 3Q, but remember R was equal to 4 times 3Q. And if we do this algebra out, which I trust that you can, but I'll still do a little bit of it right here just to make sure we're all on the same page. This 3 is going to cancel with this 36 to become 12. 4 times 3, that's 12 as well. 12 plus 12 is my total cost. Function of quantity is going to be 24Q. So that right there is step 3. Right? Step 3 is taking the K and L and plugging it into our original total cost function. So let's go ahead and look at this as a whole. So I'll make this half of the screen. And let's remember what we're trying to do. The total cost is a function of quantity. We're not using calculus. And so I gave the production function and my wage and rental rate here. At the end of the day, what we're really trying to do is find L and K as a function of quantity so I can plug back into my original total cost. And that's what we did. Step 1 was using that minimization rule that we had. So step 1, use minimization rule to solve for k. That's what this is right here. We're using this rule to solve for k. Then we took that and threw it back into the production function. We threw it back into the production function. That is step 2. So step 2, when you're solving one of these, is plug k into the production function. And remember, this is just for Cobb-Douglas. Okay, so this is just for Cobb-Douglas as a reminder. I will do one for perfect complements, perfect substitutes as well. So we're plugging that in, and then we are solving for L as a function of Q. So step 2 is plugging it into it, and then we do a couple of kind of sub-steps. We solve for L as a function of Q, and then we use that to get K as a function of Q, right? We knew that L was 1/3 Q. I knew that K was just 9L, so I just plugged in my L for the L to get us our K as a function of Q. And then our final step, which is what we're trying to do because we're trying to get that total cost as a function of quantity, right? Total cost as a function of quantity here. We're using our original total cost function, which is saying, hey, how much will it cost me to hire these many people and get this much capital? Well, it's just going to be my wage times how many people I'm hiring plus my rental rate of capital times how much capital I'm purchasing. I'm just plugging in my K and my L. I'm just plugging in my K and my L. So step 3 is plug in your L as a function of quantity and your K as a function of quantity into my total cost equaling to W times L plus R times K. And that is how, when you're given a production function and your wage and your rental rate, that you can get a total cost function. Right down here, you can see as a function of quantity. And then you can do a ton of stuff with that, which we will do. I will create a video that now shows how we can do a isoquant and a isocost if we are given a level of quantity. Again, my name is James Tierney. I own Tierney Education. I used to teach economics at Penn State University, and now I run a tutoring and academic coaching firm here in State College. If there's any other questions that you want a YouTube video for, please feel free to leave that in the comments or let me know. If any of this is confusing, again, just reach out to me. You can find me at tierneyeducation.com.